In this video, we will be discussing PFAS, a highly controversial chemical that has been debated for its benefits and their consequences. You may have heard of them referred to as forever chemicals. They have been incredibly useful, used for life-saving firefighting foams and non-stick pans, among other things. The question we'll tackle is, given the benefits and the risks, this video will cover PFAS history, its uses, structure, media claims about its benefits and concerns. Finally, it will reveal how we deal with it today, the implications, and future directions. Let's dive in.
Every day we rely on chemistry we barely notice. Non-stick pans, waterproof jackets, fast food wrappers, and even firefighting foams. All of them owe their performance to a powerful family of man-made chemicals called PFAs, short for polyfluoroalkyl substances. They definitely make life easier, but they also last virtually forever.
PFAS share a common structure, a fluorinated carbon chain joined to a polar head group. The strong carbon-fluorine bond makes these molecules heat-resistant, water-resistant, and almost impossible to break down. That's why scientists sometimes call them the forever chemicals. The fluorinated tail repels both water and oil, while the polar head attracts water. This split personality makes PFAS exceptional surfactants, spreading quickly across surfaces and forming stable films. It's also what makes them so hard to remove once they enter the environment.
PFAS stands for per- and polyfluoroalkyl substances, a large chemical family made up of thousands of compounds that all share one key feature: a strong bond between carbon and fluorine atoms, as shown here. This bond is one of the strongest in chemistry, which makes PFAS extremely stable, almost indestructible in the environment. That's why they're often called forever chemicals. Two of the best-known PFAS are PFOA, or perfluorooctanoic acid, and PFOS, or perfluorooctane sulfonic acid. Both have a long fluorinated carbon chain, the part that repels water and oil, and a functional group at the end that helps them stick to surfaces and spread evenly. This gives them their useful non-stick and water-resistant properties. In newer replacement products, scientists sometimes swap some carbon atoms for oxygen atoms, as shown here. These modified molecules are known as polyfluorinated compounds, or modern PFAS. The compound shown here is known as Gen X PFAS, or per- and polyfluoroether substances, which is a new version of a PFAS. Despite these small structural differences, all PFAS share the same problem. They don't break down naturally. Once released, they cycle through air, soil, and water, and can eventually enter the food chain through contaminated crops, livestock, and fish. So, while these compounds differ slightly in structure, their strength and persistence mean that every type of PFAS has the potential to stay in our environment and in us for generations.
Since the 1950s, companies have added PFAS to thousands of products: non-stick cookware coatings, waterproof outdoor gear, grease-proof food packaging, and perhaps most significantly, firefighting foams known as AFFF, aqueous film-forming foam. In AFFF, PFAS surfactants spread over burning fuels to form a thin, slippery film that cuts off oxygen and prevents vapor ignition. These foams save lives at airports, refineries, and defense bases worldwide. But the same chemistry that made them so effective has made them persistent pollutants even after fires have been extinguished. Over decades, PFAS from firefighting foams and consumer products have leached into soils, groundwater, rivers, and oceans. Because they dissolve in water and resist degradation, they can travel for kilometers underground and persist for decades. Scientists now find PFAS in rainwater, polar ice, fish, and human blood across the globe. This diagram shows how PFAS cycle through our environment. They begin in industry, where they're used to make non-stick coatings, waterproof fabrics, and firefighting foams. From there, they enter waste systems, firefighting sites, and eventually the wider environment: soil, rivers, and oceans. PFAS don't break down easily because the carbon-fluorine bond in their structure is one of the strongest in chemistry. This makes them highly resistant to heat, sunlight, and microbial degradation, processes that usually break down other pollutants. As a result, PFAS persist for decades, gradually spreading through air and water and building up in plants, animals, and people. They can re-enter our food and drinking water, creating a continuous cycle of exposure. Over time, this persistence means even small releases accumulate globally, earning PFAS their nickname, the forever chemicals.
Research links high PFAs exposure with several health outcomes: increased cholesterol, liver enzyme changes, thyroid disease, immune suppression, and reduced vaccine response. In communities near firefighting sites, blood levels of PFOs and PFOAs can be tens of times higher than the national average. Wildlife studies show the accumulation in fish and seabirds, sometimes leading to reproductive problems.
Unlike many pollutants, PFAS don't just stay where they're released. They cycle through air, water, and soil, forming a global contamination loop. Wastewater treatment can't fully remove them, so sludge used on farmlands as fertilizer can reintroduce PFAS to food chains. Because they're stable, even safe landfill disposal can lead to slow leaching into groundwater. Chemical manufacturers and some industrial users point out that PFAS have saved lives, preventing fires, ensuring medical sterility, and enabling advanced electronics. They also argue that not all PFAS are equal. Newer, short-chain PFAS are promoted as safer alternatives because they appear less bioaccumulative and may leave the body more quickly. In their view, the benefits outweigh the risks, especially when exposure is carefully managed. There is some truth in that. Short-chain PFAS do accumulate less in human tissue, but evidence now shows they are more mobile in groundwater and just as persistent chemically. In other words, they might move further and still last for generations.
When we weigh both sides, the environmental science community largely agrees. The persistence and global spread of PFAS makes them a long-term hazard, regardless of chain length. The chemical bond itself, the strong CF link, means these substances can't be treated like ordinary pollutants. Even if some PFAS are less toxic individually, their combined presence across thousands of compounds poses an unpredictable cumulative risk. Precaution is a must when it comes to PFAS. So what can we do? Governments and industries are acting on multiple fronts. Regulation. PFOS and PFOA are now listed under the Stockholm Convention for Global Phase-Out. Many countries are considering restricting the entire PFAS class rather than one compound at a time. Treatment. Contaminated water can be cleaned using granulated activated carbon, ion exchange resins, or high-pressure membranes such as reverse osmosis. These technologies are effective but expensive. Alternatives. Fire brigades are moving to fluorine-free foams that use hydrocarbon or silicone surfactants. Some airports have already switched successfully. Research. Scientists are exploring new destruction methods, high-temperature plasma, ultraviolet light with catalysts, and even microbes that might one day break PFAS apart. Perhaps the biggest step is prevention, designing new materials that give us performance without persistence.
You can find lots of things with PFAS in your own home. For example, makeup, conditioner, even dental floss, even firefighting foam.
PFAs have shaped our modern world, from life-saving firefighting foams to waterproof jackets. Yet their persistence reminds us that their convenience can carry hidden costs. By combining strong science and responsible industry practice, we can ensure the chemicals we design in the future don't outlive us for centuries to come.
So, to recap, PFAS are synthetic chemicals used in products like non-stick cookware, waterproof clothing, and firefighting foams. They enter the environment through industrial production, consumer waste, and firefighting sites. Once released, they spread globally through air and water and are extremely resistant to breakdown, which is why they're known as forever chemicals. While PFAS improve fire safety, medical sterility, and electronics performance, research shows they're toxic, persistent, and build up in living organisms. Even newer short-chain PFAS accumulate less in humans but remain mobile and long-lasting, raising the same environmental concerns. To reduce PFAS pollution, many countries have banned the most harmful compounds. Water treatment methods such as activated carbon or ion exchange can remove PFAS. Fire brigades are moving to fluorine-free foams, and scientists are trying to find a way to break down PFAS. It's important that we stay aware of the chemicals around us and consider how everyday convenience can impact the world we share. By understanding these risks, we can make more informed choices and support safer, more sustainable science. Thank you for watching.